Everybody. In this presentation, I want to say a few things about analogy. Now, there isn't a lot of work on analogy to the extent that one of the most widely used textbooks on AI, doesn't even have a section on analogy. They mention it that in the footnotes almost, well, in the background section of one of the chapters. So part of the reason, I think, it's because it's really, really hard. So the work I'm presenting here was primarily done by Melanie Mitchell and Doug Hofstadter. Melanie was a PhD student of Doug, and Doug is a very influential cognitive scientist. He believes that analogy is at the core of cognition. Now, clearly, whether you believe this or not, and there are many reasons to believe that this is true, clearly we solve problems by analogy. So most likely, you were introduced to the flow of electricity by an analogy to the flow of water. Also, many sort of like intelligence-like tests or admissions tests have a section of on analogy on them. So here are some examples. A book is to reading as fork is to eating, right? 8 to 4 is to, or 10 to what is the same as 8 to 4. Well, it looks like we're dividing by half of it, so that should be 5. If it takes 5 machines 5 minutes to make 5 widgets, how long would it take 100 machines to make 100 widgets? The answer, of course, is 100, right? Nah, just kidding. It's 5 minutes. All right, so let's have a look at the sort of work that Melanie Mitchell did, who, by the way, is a professor at Portland State University these days. So they were concerned about letter analogies, and you just think, yeah, letter analogies, whatever. It turns out that they're actually kind of really hard, and what we're going to be looking at is some fairly simple examples, and you can make this as complex as you want to. So let's have a look at the following letter sequence. ABC goes to DEF as VWX goes to what? So what are we going to do here? Well, we're going to look at some patterns, right? I mean, we're looking at some characters, we're looking at progressions, and so realizing, oh, wait a minute, there's ABC, DEF, and then we'll sort of like start with VWX, and we say, oh, YZ, what then? So how do we complete this thing? Well, here are some ways of doing this, right? I mean, it's not clear that there's a correct answer. There are different answers. So, we're running out of characters at the end of the alphabet, right? So we have VWX, YZ, and then what? Well, if we sort of wrap around, if we sort of see the alphabet as wrapping around, we can go to A, right? Or we sort of like take an approach that our robot takes. Well, if I can't get anywhere, I'll just sort of simply stay where I am. And so in this case, maybe we'll just say YZZ. Or we're sort of like saying, no. The alphabet is not a cycle, it's not a circle, it's sort of like is a linear structure, so we're going to bounce back. So that's what we're going to do over here. We can't go any further, so we're just going to go back. Or if you edit documents in Excel spreadsheets a lot, when we run out, we sort of like start with the characters again, we'll just double them, right? So we would go YZAA. Or somebody might just simply say, oh, no, they go to DEF. Isn't that obvious? I mean, come on. So many different ways of completing this thing, right? So how does it work? Again, it's not clear how analogy works. If it is at the core of cognition, it'll probably take quite some effort to sort of like figure out exactly how it works. But when we solve these things, we're sort of like, as I mentioned before, we're sort of like saying, okay, well, these are characters of the alphabet. There's some sort of notion of a sequence. There are successors, there are predecessors. Turns out that A is the first character of the alphabet, and then Z is the last one, at least of the alphabet that we're talking about, the English alphabet. So I think what we're doing is we're sort of like looking at patterns here, right? We sort of like observe what sort of transformations are being made as we go from here to here, and then we sort of like apply them by analogy to this one over here. Okay, so what sort of analogous transformation do we have to do to VWX to sort of like mirror the information given over here? And so there are things like letter sequences, successor and predecessor, beginning of the alphabet, end of the alphabet, wraparound, and things like this. So I'm going to show you what is called the SlipNet that Melanie Mitchell developed as part of her dissertation on Copycat. And so I know it's a little bit hard to see, but over here we have the characters of the alphabet, and we have P for predecessor and S for successor. We have letter categories, we have number categories, we have the first and the last, They're opposites. We have leftmost and rightmost. Predecessor and successor are opposites. Predecessor groups, successor groups, sameness. And so this is part of the categories that she's looking at in her dissertation, which was written a long, long time ago, I think in 1990. There are a couple of aspects to her system that she developed. There's a slipnet that I showed you over here, and it's called slipnet because these are all very, very fluid. I'll give you a demonstration here in a moment, and so I'll understand a little bit more of why that is called a slipnet. Then there's a workspace. So over here, we're sort of looking at different possible answers and evaluating them. And then over here is the code rack. I should show you some of the code, or codelets as she calls them, that go into the code rack. The architecture is kind of similar to expert systems in the sense that we have some knowledge, some background knowledge, we have some working knowledge, and then we have some code that operates on this thing. There's never some answers appear over and over again, but it's not guaranteed. So there's a high amount of, well, a certain amount of probability involved in here. Temperature. I don't know how much you know about optimization algorithms. So there's this idea of simulated annealing, where as you know, it comes from steel. Steel anneals when it gets you sort of bring it hot and then you let it cool down slowly, and so like all the atoms in it sort of get pretty cozy, and that's a good thing. But the idea is you might ask the system or offer the system to do lots of crazy things, try lots of different things early on, but eventually sort of like cool down a little bit and sort of like settle in on some of the better choices. So before I show you the codelets, let me sort of like, let's do a quick demonstration. So this is some code. Her code, I think, was written in Lisp or Scheme, and so this somebody re-implemented it in Python. And I put a link on our website to sort of like show you where you can find the code. So let's do something fairly simple. ABC goes to ABD, and then what does DEF go to? Okay, so DEF goes to DEG. So if we go back to this thing here, we will see that, you know, that kind of makes sense. You know, we have AB, AB, DE, DE, and then C goes to D, F goes to G. So that's DEG. All right, so there you have it. Well, let's try the one that we tried earlier that I wrote up in the slides. ABC goes to DEF, and then what was it? VWX goes to what? YZA? We don't know. Let's find out. Oops. Move this up a little bit. Run. So this thing is going to run a little bit. And so in the meantime, I'm going to say a few things about some of the codelets. Actually, let me start with this one over here. So this one is a bottom-up bond scout. It has no arguments. And so a codelet of this type chooses a pair of adjacent objects and see if there is any bond that can be made between them. Say successorship, so AB, right? Oh, that's pretty cool. Again, you can have A, you know, PR or something like this, and so there wouldn't be an immediate successorship. Here is a bottom-up description scout. A letter of this type chooses an object, say A and ABC, and a description of that object, say letter category, and sees if any new description can be attached to this object based on the has property link of the slipnet. Okay, so it could look for any conceptual close properties to A. So if first were seen as close enough to A, the codelet could propose a new description, alphabetic position first. Okay, and so again, it would then post this piece of information that it knows something about, and other codelets might do something with this thing to sort of look for bigger patterns, if you wish. This is a direction scout, you know, looking for spatial directions. So the idea is that we take the analogy problem, and then we add more information to it. And some of the information is very low level, and some of them looks for higher and higher patterns. So if you remember, we looked at convolutional neural networks, and we sort of like described them as looking for initially fairly low patterns and sort of like building on them. That's a big deal in AI, to sort of like hierarchically increase, if you wish, increasingly looking for patterns. Well, let's see whether the system came up with a solution. So VWF. Well, that's interesting. So let's have a look at that. So again, VWF. So what it did is it just simply said, okay, I can't go from VWX. So, I mean, I guess I was hoping that it would do YZ, potentially F, but it didn't do that. So it did VW, so it replaced the X with F. So I don't know whether this is the best choice, but that's what it did. Alrighty, folks, that's it on analogy. Again, there's not a lot of work, so like that is lecturable, if you wish. I did post a bunch of links to some of the articles by Melanie and Doug, and by Doug, as well as one by Melanie where she sort of looks at the analogy making abilities of GPT-3. So please have a look at some of these things and see whether maybe there's some work there that you want to do in the future, do a PhD and revolutionize what we know about analogy. I'll talk to you then. Bye.